All right, let's get into our next section here in Domain 3 for security engineering. The engineering life cycle using security design principles. Let's start by talking about disciplinary methods for systems engineering models. And we're going to talk about a lot of different models in this section here, a lot of different frameworks. Systems engineering interdisciplinary approaches to translating users' needs translating the user's needs into the definition of a system, architecture, and design through iterative processes resulting in operational systems. What are we talking about here? We're talking about systems as a whole. It could be an application system. It could be a functional system to provide a service in a network or whatnot. And we're going to look at different frameworks and models that allow us to design these systems. The first one we see mentioned here is the International Council on Systems Engineering. That is a nonprofit organization based on systems engineering. They have, tens of thousands of members, I guess. And they have conferences and whatnot to discuss, different aspects. I think they're based out of California, actually. Different aspects of system engineering. They do publish a couple of different periodicals, and they do work in collaboration with organizations like IEEE, specifically the Computer Society, and they are a member of the Federation on Enterprise Architecture for Professional Organizations. Is that important to know? Probably not. Not really important to know, but it is relatable to what we're going to be talking about, and we are going to reference some different standards as we go through this section here. So it's important to kind of understand, what organizations might be involved in establishing these standards and so on. ISO IEC, the International Organization for Standardization, and the International Electrotechnical Commission established 15288, which is in fact the technical standard for systems engineering. And it's going to cover things like life cycle stages of planning and designing systems. It's been adopted by the Department of Defense and the federal government, and it does represent essentially practices and processes in systems engineering. There are 30 processes that are grouped basically into 4 different categories. We can see the 4 categories listed here: agreement processes, organizational product enabling processes, technical management processes, as well as other technical processes. There are 2 agreement processes as well, acquisition and supply processes. And then we have 6 kind of organizational project enabling processes as well. As I read this or kind of reference this, it should kind of make sense generally what these processes are going to be dedicated to, even though we don't necessarily know them specifically. A lifecycle model for management, infrastructure management, portfolio management, human resources management, quality management, knowledge management, and so on. We also have some technical management processes that are defined: project planning, project assessments and control, how do we make decisions, risk management, configuration management, IT or information management, quality assurance components, and so on. I'm not going to go into the specifics of the 14 different, I forget what they call them, the technical processes, or it includes things like test and integration and verification and design and validation and so on. But you're going to see as we go through each of these frameworks in each of these models that they all kind of have similar structures, just like our risk management framework had. That is one of the things about this particular exam that they do love, or at least this CBK, that they do love to discuss, and that is frameworks. We tend to focus on the frameworks that are kind of housed in the United States, but the same kind of frameworks exist all over the world. We will talk about the maturity model integration framework. We'll talk about the SDLC framework, the systems development lifecycle framework, and so on. All right. Let's start by talking about one that they do love to test on, which is the V model. This one is extremely popular. It's primarily used in developing software applications. It is called the V model. I'll show you the graphic and then I'll come back and hit the bullet points here, but this is the reason it's called the V model. We have a project definition phase, and these are the components of the project definition phase. And then we have a project test and integration phase, and these are the three components of project test and integration. And then we have verification and validation, and we can kind of maintain that cycle as necessary to go through the steps. All right, so that's the graphical representation. The idea here is that we have a way of representing systems development life cycles. The concept of operations, the requirements and architecture specification, detailed design, those are the project definition components. And then we have the integration test and verification, system test and verification, or validation, I should say, and operation and maintenance, which are the project test and integration components. The V model itself is used to produce kind of this development lifecycle model. It is somewhat generic, I guess, in the definition of each of the phases, and they kind of make sense what each of the phases represent, right? The left side of the V is a decomposition of requirements and the creation of system specifications, kind of the design, if you will. The right side of the V represent the integration and the parts of validation. So that would be kind of the implementation component, if you will. All right. There are, it actually was developed by the Germans as a project management method for the German government, very equivalent to, I don't know if you guys have ever heard of the Prince 2 model, but this particular model is kind of more specific to software development. The key component of the V model was to make sure that during the software development process that we had proof that the products from the left side of the V were acceptable for testing and integration within the organization based on the right side of the V. The V model is kind of widely seen as a software development process model. The U.S. also has kind of a standard V model, which they kind of adopted from this as well. All right. Now, one of the takeaways here, let me go ahead and go into the pretty diagram, is that there has to be a component of validation versus verification. All right. Sometimes you can say, and that's the top arrow at the top there, verification and validation. Validation is different than verification in a sense of validation is, are we doing what we expected to do? Are we building the right thing, basically? And verification would be, are we doing it right? Does that make sense? So validation would be, does it meet the requirements? Kind of our concept of operations, the requirements and architecture. And then verification is it performing as expected? So the validation is really just the assurance that the product, the application, the service, or the system, however this model is being applied, meets the needs of what we defined, with the customer or with stakeholders, and it would often involve some sort of acceptance and suitability testing with those individuals, those customers. Whereas verification is the evaluation of whether or not the product or the application or the system complies with requirements like regulatory requirements, specific specifications, or imposed conditions that we imposed in the initial design. And this is kind of more of an internal process as we're doing the development. What are the objectives of this model, or really just any model in general? Minimize risk to the project, right? We want to make sure that we have transparency for the project. We have specific controls in place by using a standardized approach that's going to correspond to results. We have individuals that have roles and responsibilities. And hopefully, if we deviate from this, it's going to provide us early recognition of those deviations, and we can take action. We also want to ensure quality of the project, right? And again, I'm talking about this in reference to the V model, but this would apply to really kind of any standardized model. In any kind of standardized process, we want to make sure that the results are have the desired output, that they have the desired quality. There could be kind of key points along the path, like interim results that can be checked, which then would allow us to identify deviations as well, which is then ultimately going to improve verifiability of the project itself. If we can do that, hopefully we're reducing the total cost over the entire life cycle of the system, because it addresses all of the needs that we have within that system, right? For not only future-proofing the components of that system, making sure that they're going to provide adequate operation, maintenance of the system can be calculated. All of this can be done based on applying these standards. And then, of course, well, I wouldn't say of course, but certainly the last thing would be just adequate communication. We have ways of describing the elements in terms that everybody understands, the stakeholders, the end users, and so on. And so we know that we are providing something that that meets everybody's needs. Okay. So verification phases, these are kind of just the breakdown of each of those phases. We have requirements analysis. The first step in the verification process, first step in verification process is to process requirements of the system that is collected by analyzing the needs of the users. We're concerned with establishing what the ideal system has to do, how it has to perform, but we don't determine how it's designed or built yet. So this is kind of our high-level representation of what the system is supposed to do. Then we get into our system design phase. The systems engineers analyze and understand the business of the proposed system by studying those requirements. We figure out the possibilities and the techniques on how user requirements can be implemented. Then we go into architecture design, designing of the computer architecture and the software architecture, which can then be referred to as our high-level design. Our baseline in selecting the architectures should consist of different modules, a brief functionality of each of those modules, interface relationships, how those modules interact, what the dependencies are between those modules, what kind of database tables, architectural diagrams, technologies, etc. that we're going to have to incorporate. And then we'll start to design the low-level design, which is breaking up the design elements into smaller components designing each of the individual modules so we can start coding those modules. The low-level design document or the program specifications contain detailed functional logic of those individual modules. All right, unit testing, or what we call unit test plans, get developed during the module design phase. Obviously, unit testing allows us to isolate or identify bugs in the design at the code level or at the unit level. Integration testing is developed during the architectural design phase. This is going to test and verify that the units that we created, they're tested independently, but we want to ensure that they can coexist and communicate amongst themselves. That's why it is called integration testing, because we're testing the integration of the individual units together. The test results get shared with the customer team. The systems testing developed during the systems design phase. Systems test plans are composed by clients' business teams to ensure the expectations from the application development are met. The whole application in this case is tested for functionality, interdependency, and communication. We verify the functional and non-functional requirements have been met for the overall system. And then finally, user acceptance testing, the UAT. We have the user acceptance test plans, which are developed during the requirements analysis phase. And this is composed by business users, and the UAT is performed in the end user environment that resembles the production environment using realistic data. This verifies that the delivered system meets the user requirements and the system is ready for use in real time. This particular slide, I think, holds some value, particularly for the exam. Understanding the different terminology here is what's important, not necessarily how it applies to the V model or specifically what stages of the V model these things take place, but understanding what a unit test is, what an integration test is versus a system test versus UAT. Those are terms that you would most likely see on the exam. Whether or not you know that the systems testing happens during the systems design phase of the V model experience, well, that's a different scenario. Okay. Systems engineering technical processes. We do our requirements definitions, our requirements analysis, our architectural design, implementation, verification, validation, and transition. This is not related to the V model, but you can see there are a lot of similarities between these bullet points and what we saw in that V model. All right. As far as the engineering management process, we have decision trees that we use to make our decisions throughout the engineering life cycle. We have technical planning aspects, technical assessment aspects to make sure systems meet planned requirements. We have requirements management phases, risk management phases, configuration management, interface management, and technical data management. Again, you're not going to have to recite these bullet points specifically for the exam. And most of these bullet points probably make sense from a chronological order as well as the strict definition of the term. We understand what each of these phases represent. All right. We always want to make sure that security is a consideration in our design efforts, right? Security should be an element of the configuration. We have to ensure that we have overlapping protections. We'll certainly talk about how we provide that of those overlapping protections based on system security. But we are protecting people, processes, technology, operational aspects of systems, and so on. A single system as a whole cannot be secured unless all of the interconnecting systems that are connected to that single system are also secured. So having overlapping protections, or what we would typically define as defense in depth, means that a compromise of any individual protection approach will not compromise the system as a whole because we have secondary protection mechanisms in place. We need to make sure that we have user training and awareness, policies and procedures, redundancies built in for those protection mechanisms for the effective protection of the IT resources. Okay. NIST Special Publication 814, the General Accepted Principles and Practices for Securing Information Technology Systems, outlines those foundational aspects. And we're going to break this down a little bit over the next couple of slides. There are 8 different principles and 14 practices. And as we look at these, you're going to say, well, I guess that kind of makes sense. That's what I would expect for a framework that discusses securing information technology assets. So let's take a look. All right. Here we are looking at the initiation. The need for the system is expressed, right? Why do we need this system? What is the purpose of the system? That would help us identify, in essence, what how many resources we're going to allocate to developing this system. What level of security or protection we're going to apply to that system, and so on. Development or acquisition, we move into that phase where the system is designed or components of the system are purchased, programmed, customized, developed, or constructed. We determine the security requirements, and during this phase, we will incorporate those specifications into the system, either by defining a request for proposal or request for information from vendors to make sure that they meet those specific requirements, or simply designing those requirements in-house into the system itself. Implementation. The system is then tested and installed. The installation of the system, the security testing, the certification and accreditation of the system takes place. And then we move into the operation and maintenance phase, where the system does what it's supposed to do. Components of the system can be modified if we want to supplement or augment the system with additional hardware or software. If we find that there are weaknesses or the system isn't providing the appropriate function, we will also look at security operations, administration, operational assurance. There's an auditing component and a monitoring component as well. And then finally, at the end of the system lifecycle, disposal of that system in a secure manner, right? The hardware or software, moving it to a different location, archiving the information, discarding the system, or destroying that information. All right. Now, if we look at Special Publication 827 in more detail, there are essentially, these are the principles that we were discussing previously. If we look at these principles, again, they'll make sense, right? Security foundation. Establish a security policy as the foundation for the design. Principle 2, treat security as an integral part of the overall system design, not as a secondary component, right? We want to make sure that security is considered to be a major component of the overall design. Principle 3, clearly delineate physical and logical security boundaries governed by the associated security policies. The reason we would want to do this, obviously, we're going to provide different controls for the physical security boundary, meaning how the system is maybe physically attached to other systems or to the network, versus logical security boundaries, which might be boundaries that are defined within the system, interaction between the modules of that particular system or the APIs or the application within that system. Principle 4, ensure that developers are trained in how to develop secure software. And then our risk-based component, right? Reduce risk to an acceptable level. Assume external systems are always insecure. Identify potential trade-offs between reducing risk and increased cost, and decrease in other aspects of operational effectiveness, and decreases, I should say, in other aspects of operational effectiveness. Meaning, as we add security, we're going to increase cost, but we may also increase complexity of the system, which might affect operational effectiveness or make it a little bit more cumbersome to use or difficult to use, and so on. Implement a tailored system with security measures to meet the security goals. Protect information that's being processed at rest or in transit. Consider the custom products to achieve adequate security if off-the-shelf products are not going to be sufficient. And then try to protect against all likely classes of attacks. Not entirely possible, but something to consider. All right. Ease of use, principle number 12, base security on open standards for portability and interoperability. If we're developing an entirely custom system, it's going to be a challenge to integrate that system with other applications or other systems that may be open standard. We're not using open standard protocols. You might think, well, open standard means everybody knows what's happening, but open standard protocols and processes have also been vetted. And they tend to be a little bit more trustworthy than custom applications. Principle 13, use common language in developing the security requirements. Principle 14, design security for regular adoption of new technology, including a secure and logical technology upgrade process. And then principle 15, strive for operational ease of use. Okay, there's only about 80 of these, so no, I'm kidding. Increase resilience, availability, right? That's one of the cornerstones of the CIA triad. Principle 16, implement layered security, no single point of vulnerability. Design and operate the IT system to limit damage and to be resilient in response to negative events, all right? Provide assurance that the system is resilient in the face of expected threats. Limit or contain vulnerabilities. All right. Increase resilience continued. Principle 20, isolate public access systems from mission-critical resources. Use boundaries to separate systems and network infrastructures. Design or implement audit mechanisms to detect unauthorized use and to support incident investigations. Principle 23, develop or exercise disaster recovery procedures to ensure appropriate availability. Reduce vulnerabilities, strive for simplicity. In simplistic design, it's easier to assess a platform and to understand how that platform is going to interact. Minimize the system elements to be trusted. Implement least privilege. Do not implement unnecessary security mechanisms that really don't achieve any perceivable goal. Ensure proper security in the shutdown or disposal of the system. Identify and prevent common errors and vulnerabilities. All right, the last one, design with the network in mind. Principle 30, implement security throughout through combination of measures distributed physically or logically. Formulate security measures to address multiple overlapping information domains. Authenticate users and processes to ensure the appropriate access control decisions both within and across domains. Now we're talking about the system as a whole, as it not only operates internally, but as it operates with other systems within the enterprise. Use unique identities to ensure accountability. All right. So the last slide here, security policy documents your security requirements of the organization. Kind of a general statement, but very true. A specification that describes the rules for implementing the security policy to support or enforce that security policy. We can use a formal security model. We've already seen, I guess the V model is not really a formal security model. We can use NIST publications, special publications, or other models that we're going to see actually over the next section to define security in measurable terms with what we're implementing. But the policy itself is, what are the requirements for security? The model itself is, how are those requirements being translated into implementable and auditable technical specifications. By definition, the policy is what we're trying to achieve. The model itself is how we are going to achieve that. We will look at different systems level security architecture models over the next couple of sections. All right.